Here's a radioactive decay problem. Radioactive decay follows first-order kinetics. And we know something about first-order kinetics. There are constant half-lives. They even give us the value of the half-life. Let's use the half-life formula that we know for first-order reactions. It's the natural log of 2 over k, and if you work that out as a decimal, 0.693 over k. They're telling us that the half-life of 14.3 days is equal to 0.693 over k. We can use that to find the value of k. K would be 0.693 over 14.3, and if you pull out your calculator, that works out to be 0.0485. Next, they're asking us a question about how long it takes for 98% of a sample of phosphorus 32 to decay. Notice that they don't give us the initial concentration, and they don't give us a concentration at the time that they want us to find. But they give us the percentage, and that percentage will enable us to find the mathematical relationship between the initial concentration and the concentration at the time that we're interested in finding. And furthermore, since it's first-order kinetics, the percentage is just as good as if they had given us a real set of numbers. For the sake of simplicity, let's say that the initial concentration of, I'm going to use A instead of phosphorus, it was 100 molar. And then if 98% of that initial amount decays, that is, goes away, then the concentration at the time that we're considering would be only 2% of what you had begun with. 98% went away, only 2 is left. Then we can apply the integrated rate law for a first-order reaction. If we plug in the concentration of A, our known value for the rate constant K, and we're going to solve for time, we come up with an expression that looks like this. And now it just becomes an easy algebra problem. Pull out the calculator, start simplifying some of these expressions. Natural log of 100 is 4.605. And if we solve for time, we get 80.66. And by the way, they've been working with days as the time unit. So that's what we come up with as the time unit, days. 80.66 days.